have uh, in white box testing, we have to uh, test either statements using statement coverage, condition coverage, and then we came to composite coverage, okay, branching coverage. So here you can see in last example itself, you can see that branch coverage is the most efficient way to test all the almost all the statements with perfect test cases. So in order to build test cases, number of test cases, we need to find number of conditional statements, number of path we need to cover to, to cover the entire program, entire module. We need to find a path. Okay. So what we are going to do, we are going to make a test cases. We are going to test the internal structure of our source code modules or program. So we cannot execute entire statements. So just like running a test randomly on every statement doesn't produce results as we have seen in examples. So we need to find path that can lead us to test all the basics, all the statements of the source code with perfect test cases. So we need to understand path. Okay. Path through a program is a node and its sequence from starting node to terminal node of the control flow graph of the program. Here we can see this is the path. This is the node and edges. So we can have two paths here. One from 1, 2, 3, then 5. 1, 2, 4, and then 5. 1 to 6. 1, 2, 3, and then 1 again. You can see this. We have 4 paths. Okay. So this is the path that we choose either based on test cases. The path may be varied. There can be more than one terminal node in your program. Writing the test cases to cover all the paths of a typical program is impractical. For this reason, the path coverage testing does not require coverage of all paths, but only coverage of linearly independent paths. Okay. So what is a linearly independent path? A linearly independent path is any path through the program that introduces at least one new edge that is not included in any other linearly independent path. Okay, here we have paths. Okay, 1, 2, 3, and then 4. 1, 2, 3, and then 5. Okay, compared to this path, 1, 2, 3 is a path, and you can see 5 is another node added. So there is an edge added to this path. So we can say that it is a linearly independent path. At least one node needs to be added. If a path has one new node compared to all other linearly independent paths, then the path is also linearly independent path. Okay. Because any path having a new node automatically implies that it has a new edge. Thus, a path that is subpath of another path is not considered to be linearly independent path. Basically, a path which actually introduce a new node is called as a linearly independent path. We know about control flow graph already we have seen. The path coverage testing does not require coverage of all paths, but only coverage of linearly independent paths. Okay. Cyclomatic complexity. So in order to build test cases, we need to find number of linearly independent paths available in the module. Okay. So MECAP's cyclomatic complexity defines an upper bound for the number of linearly independent paths in the program. Okay. The MECAP cyclomatic complexity is very simple and easy to compute. Here we have three methods. Three methods. One, two, three. Three methods to find out number of linear independent paths in program. In I think 2019, 21, I think there was a question, reading comprehension question was asked from complexity, this cyclomatic complexity. Like they given flow graph and a pseudocode and ask question. So now find number of linearly independent paths and what is the edge, like the question. So method one, given a flow graph, the cyclomatic complexity can be here vertices V, vertices E edges, vertices E edges. So we're going to calculate this cyclomatic complexity. Edges minus node plus 2. Edge minus n node plus 2. Number of edges minus number of nodes plus 2 will give you the cyclomatic complexity. Here we have in this program, in this cyclomatic graph, we will apply the same. Edges, vertices are equal to edges minus node plus 2. So number of edges includes number of edges. Let's see, 1, 2, 3, 4, 5, 6, and then 7. Number of nodes, 6 nodes. Okay, so edges 7 minus 6 plus 2 will give us 3. Okay, this is the cycle number of linear independent parts of this CFG control flow. We have then method 2. So remember this, edges minus node plus 2 will give you number of linearly independent path of the control flow graph. Next program, next method, total number of bounded areas plus 1. Total number of bounded areas plus 1 here, which means that bounded means repeated. Bounded means the same. Bounded means repetition or loop, we will say. Bounded means repeated or iteration. We say that number of bounded areas plus 1. You can say here 1, then 2. Okay, this one, and then we can say this one, 2. Okay, we can see conditional branch here. So 2 plus 1 again will give us 3. This one came from this outer bound. You can see this one as an additional bound given when the program exists. Okay, outer bound. And then third method can be easily computed by number of decision statements of the program. Okay, so number of decision statement of a program, then is equal to n plus 1. If n is the number of decision statement, then cyclomatic complexity would be n plus 1. In this example, we have number of conditional statements. We say from the program itself, we can say conditional statement 1 while and then if. So 2 plus 1 will give us 3. So number of conditional statements plus 1. So method 1, number of edges minus node. Number of edges minus node plus 2. And then another method, bounded, number of bounded areas plus 1. Another method, number of conditional statements plus 1 will give us cyclomatic complexity of the program, which give us upper bound, maybe the upper bound of linearly independent path of your control flow graph. Okay. Then mutation testing. Here there is a mutant in the test cases. Okay, there is an initial test case was given, and there is a mutant program. Okay. The idea behind mutation testing is to make few arbitrary changes to a program at a time. Each time the program is changed, it is called mutated program. And the changes affected is called mutant. Again, we make a test. Okay. We conduct a test using test cases we have built. After that, we are going to change some changes to the program. That program is called mutant. Again, we are going to test the same program with the test cases. Okay, again, a mutated program is tested against the full test of the program. If there exists at least one test case in the test suite for which mutant gives incorrect result, then the mutant is said to be dead. If a mutant remains alive even after all the test cases have been exhausted, the test data is enhanced to kill the mutant. Okay. The major disadvantage of mutation-based testing approach is that it is computationally very expensive since large number of possible mutants can be generated. So just we are going to change the programs and change the content of the programs and test it. If it produces same results, then we have to change the test cases to kill the mutant. Then debugging, integration, and system testing. Now we have completed black box and white box testing. Next, we can move to debugging. So integration and system testing. So as a unit, what we have done now, as a unit, a module is working fine. As a program, yep, as a single unit, a program is working fine. Now we have to integrate the programs and test against whether they are working fine during integration. Here, once errors are identified in the program code, it is necessary to first identify the precise program statements responsible for the errors and to fix them. Identifying errors in a program code and then fix them is known as debugging. Approaches include brute force method, most common method of debugging, and least efficient method. Here, program is loaded with print statements to print all intermediate values with the hope that some of the printed values will help to identify the statement in error. This approach becomes more systematic with the use of symbolic debugger, also called as source code debugger. Okay. Then backtracking. Here, beginning from the statements at which an error symptom has been observed. Okay. What we are going to do is we are going to backtrack. We are going to search back. Okay. Beginning from the statement at which an error occurred, observed, and then the source code is tracked backwards until the error is discovered. Okay. Then cause elimination method. List of causes which could possibly have contributed the error symptoms is developed and tests are conducted to eliminate each. A related technique of identification of error from error symptom is software fault key analysis. Fault key analysis. Program slicing. We are just going to cut down in half. Similar to backtracking, here search space is reduced by defining slices. A slice of the program for a particular variable at a particular statement is set of the source lines preceding the statement that can influence the value of the variable based on where the error occurred. We are going to slice the program, which may affect the variables. Okay. Then guidelines, we have given guidelines. Many times debugging requires thorough understanding of the program design. Trying to debug based on partial understanding of the system design and implementation may require an inordinate amount of effort. Okay. Debugging may sometimes even require full redesign of the system. In such cases, a common mistake a novice programmer often makes is attempting not to fix the error but its symptoms. One must be aware that possibility that an error correction may introduce new errors. Therefore, after every round of error fixing, regression testing must be carried out. Okay. After every round of error fixing, regression testing must be carried out. Program analysis tools. We have 3 types of tools. Okay. To understand the characteristics of a program, such as size, complexity, adequacy of commenting, and then adherence to programming standards. Okay, so either static analysis tool, dynamic analysis tool, static program analysis tool. Okay, okay, we can no problem. And then integration testing. Till now we have tested modules as a unit. Modules as a unit. Now these modules is going to interact with each other. Now we have to integrate this modules. Integration test approaches include big bang approaches, bottom-up approach, top-down approach, or combination of both bottom-up and bottom-up, top-down approach in mixed approach. In big bang integration approach, all the modules are integrated at one time. All the modules integrated at single time, at the same time. The problem here is, if there is an error, we don't know which part, which integration, or which module has errors. Okay. Here, all the modules of the system are simply put together and tested. Okay. This technique is practicable only very small systems. The main problem with this approach is that once an error is found during the integration testing, it is very difficult to localize the error, as the error may potentially belong to any modules of being integrated. Therefore, debugging errors reported during Big Bang integration testing are very expensive to fix. Then bottom-up approach, from sub-components to weaker components. Okay, we already decomposed the program. We already decomposed entire software into modules. Okay, now we are going to integrate each module sub-components to bigger components. Each subsystem is tested separately, and then full system is tested. A subsystem might consist of many modules which communicate among each other through well-defined interfaces. Primary purpose of testing each subsystem is to test interfaces among various modules making up the subsystem. Both control and data interfaces are tested here. Here, important point to be noted, in pure bottom-up testing, no stubs are required. In pure bottom-up testing, no stubs are required. In pure bottom-up testing, no stubs are required, which means like we are going to integrate subsystem, which is functions. So during integration, function parameters, function calls is integral part of the testing. Whether your module is returning values properly, sending values properly, or referencing the variables properly, those are integral of bottom-up testing. So the stub procedures act as a function calls to produce exact results. No is not needed. The disadvantage of bottom-up testing is complexity that occurs when the system is made up of large number of small systems. Then extreme case corresponds to the Big Bang in top-down integration testing. It starts with main routine and one or two subordinate routines in the system. After top-level skeleton tested, the immediately subroutine of skeleton are combined with tested. Okay, here, the driver modules are needed. The driver modules are not needed here. A pure top-down integration does not require any driver routines. Driver routines which provides access to global variables. Okay. Like in a table lookup format, in the table we just give results in global variables. We are going to start with the main. We are going to start with main routine. So global variables is already placed. So there is no need for any driver modules. Okay. Okay. Disadvantages include that many times it may become difficult to exercise top level routines in the design manner, since lower level routines perform several low level functions such as input output. So we need stub procedures. Then mixed integration strategy, it can be followed, also known as sandwiched strategy, sandwiched testing. Okay. Either we can start from the top where main components have been tested, and also we can test from subsystems and go further, whichever is available first. Okay. Then phased with incremental testing. Here phases means that Either a single modules can be tested or related modules that produces or worked on some task. Okay, we can make a phase on our testing, meaning that collective or group of modules that work on the same task or produce the same uh, results one after another. So that can be tested as a single part. In incremental integration testing, only one new module is added to the partial system each time. In phased integration, a group of related modules are added to the partial system each time. Okay. And then system testing. We already knew that alpha testing, beta testing, and then acceptance testing. Alpha testing, testing carried out by the development organization. Beta testing, testing carried out by selected group of friendly customers. Acceptance testing performed by the customer itself to determine whether to accept or reject the delivered system, delivered product. In each of the above type test cases, various kind of test cases are designed by referring to the SRS. Broadly, these tests can be classified into functionality and performance testing. The functionality test the functionality of the software to check whether it satisfies the functional requirement as documented in the SRS document. The performance test tests the conformance of the system with the non-functional requirements of the system. Performance testing performance testing is carried out to check whether the system needs non-functional requirements, meets non-functional requirements, meets. Okay. There are several types of performance testing here. All performance tests can be considered as black box tests. All performance tests can be considered as black box tests. Trust testing, volume testing, trust testing considered like a result portal where only it is not executed often, but free, but peak at a single time. Volume testing, configuration testing, compatibility testing, regression testing, recovery testing, maintenance and documentation and usability testing. All these are black box testing. All these are black box testing. Trust testing, also known as endurance testing, evaluates the system performance when it is stressed for a short period of time, just like a result portal. So right now, at this time, no one, uh, no one, not even single person will visit the result portal of Bharatiya University right now. Maybe one or two, but during the result time, almost all will visit this particular result portal. So stress tests are black box tests which are designed to impose a range of abnormal and even illegal input conditions so as to stress the capabilities of the software. Input data value, input data rate, processing time, utilization of memory are tested beyond the designed capacity. Here, for example, an operating system is supposed to support 50 multi-program jobs. The system is stressed by running more than 50 jobs simultaneously. A real-time system might be tested to determine the effect of simultaneous arrival of high priority interrupts. Okay. Stress testing is very important for systems that usually operate below the maximum capacity but are severely stressed at some peak demand hours, such as peak demand hours, such as we can say ticket booking applications, such as. For example, if the non-functional requirement specification states that the response time should not be more than 20 seconds per transaction, where 60 concurrent users are. Then during the stress testing, the response time is checked with 60 users working simultaneously. Volume testing concerned with data structures such as arrays, queues, tags, have been designed to successfully extraordinary situations. A compiler might be tested to check whether the simple table overflows when a very large program is compiled. Configuration testing to analyze system behavior in various hardware and software configurations specified in the requirement, such as version control. Sometimes Systems are built in variable configuration for different users. For instance, we might define a minimal system to serve a single user and other extension configuration to serve additional users. The system is configured in each of the required configuration and it is checked if the system behaves correctly in all required configuration. Compatibility testing includes it requires when the system interfaces with other type of system. We have to check the interface. For example, if the system needs to communicate with large database system to retrieve information, compatibility testing is required to test the speed and accuracy of the data retrieved. Regression testing, we seen that if one error is fixed, which can lead to other bugs. Okay. This type of testing is required when the system being tested in an upgradation of an already existing system to fix some bugs or enhance functionality performance. Regression testing is the practice of running an old test suite after each change the system or each bug fixed to ensure that no new bugs have been introduced due to change or bug fix. However, if only few statements are changed, then the entire test suite is no need to run. Only those test cases only need. Recovery testing, how fast it is. We will see the reliability later, how fast the system recovers, what is the failure time, what is the amount of time needed to fix the problem. Those are applicable. Recovery testing tests the response of the system to presence of fault, loss of power, devices, services, data. The system is subjected to loss of the many resources, mentioned resources, and it is checked if the system recovers satisfactorily. For example, the printer can be disconnected to check if the system hangs, or the power may be shut down to check the extent of data loss or corruption. Maintenance testing addresses the diagnostic programs, and other procedures that are required to be developed to help maintenance of the system. It is validated that artifacts exist and they perform properly, like troubleshooting methods. Okay. Documentation testing. It is checked the required user manual, maintenance manuals, technical manuals exist and are consistent. The requirements specify the type of audience for which a specific manual should be designed. Then the manual is checked and compliant. Then usability testing. Concerned with checking the user interface to see if it meets all user requirements concerning the user interface. During usability testing, the display screens, report formats, and other aspects relating to user interface requirements are tested, such as message boxes, notifications, pop-up windows. So, like reports generated and downloading, uploading, those kind of things. And then other method, error seeding. Okay, here what we are going to do, we are going to seed the errors to find new errors. What we are going to do is we are going to seed errors. Then we check whether test cases is finding those error or not. Okay. So we can see that let n be total number of defects in the system and let small n of those defects found by the test. So n, let S be the total number of seeded defects and the smallest of those defects can be found during testing. So you can say defects still remaining after testing is equal to total number of defects in the system minus number of defects found by the testing is equal to number of errors found in the testing multiplied by total number of seeded errors minus defects found. Total number of seeded errors minus number of errors found during testing system divided by total number of, smallest is the smallest, divided by number of defects found during testing. Another method, regression testing, we already see. Okay. Those are about testing. Okay. Is any questions regarding testing? Any questions regarding testing? Very important. the frequent questions will be asked from testing alone. At least 2 questions we can expect. Guaranteed 2 questions from the testing alone. Software engineering is a unit which comprises 10 questions. We can expect 2 questions from testing alone. Any doubts on testing? We can move to the next section, which is software maintenance. Okay, we have 3 types of maintenance: corrective maintenance, adaptive maintenance, and perfective maintenance. Here, corrective maintenance refers to the errors that are found, observed while the system is in use, and then adaptive maintenance is to enhance or change of hardware requirements. So the interface, so we are going to make changes in the software product. Then perfective maintenance based on user's requirement, uh, functionalities, we have to make adjustments. Okay. Problems associated with software maintenance. Okay. Here, problems associated with software maintenance is, you can see that almost development cost, the total cost is 100 rupees, development cost is 40 rupees, and maintenance cost is 60 rupees. So 60% of total software life cycle, we will focus on maintenance. It is much more expensive than what it should be and takes more time than required. In software organizations, maintenance work is mostly carried out using ad hoc techniques. Here, okay. Software maintenance has very poor image in the industry. Therefore, an organization often cannot employ bright engineers to carry out maintenance work. Even though maintenance suffers from poor image, the work involved in is often more challenging than development. During maintenance, it is necessary to truly understand someone else's work and then carry out the required modification. And another problem with the maintenance is that majority of the software products needing maintenance are legacy products. Here, legacy products means that are developed like those software, when those software developed, uh, they used hardware configurations. That hardware is not even available now, like that. Okay. Okay. Software reverse engineering and then software re-engineering. There are 2 methods to understand: software reverse engineering, software re-engineering. In software reverse engineering, code. Okay. There is a document. We have a SRF document. Against the SRF document, we will check the code, and then we will check the code. During check the codes, we have to name the variables, give variables meaningful names, comments, add comments. Okay, those needs to be done, and then module specifications, functionality of the module needs to be find out. And then design, extracted design. We have to extract design from modules such as logical DFT diagrams, class diagrams, UML integration diagram. Then requirement specification document is built. So what we do is, basically we will start from requirement specification and then code. In software reverse engineering, we analyze the code, then we specify the modules. From the modules, we extract design of the system, and then we will file requirement specification. This is possible for errors. This is possible for the system with the failures, maybe less than 30%. Okay. Then okay, legacy software products already. Okay, legacy software products. It is prudent to define legacy system as any software system that is hard to maintain. The typical problems associated with the legacy systems are poor documentation, unstructured, lack of personal knowledgeable in the system, in the product. Many of the legacy systems were developed a long time back, but it is possible that recently developed system having poor design and documentation can be considered also be a legacy system. The activities included in software maintenance projects are not unique and depend on several factors such as extent of modification the product required, resources available to the maintenance team, conditions of the existing product, how it's structured, how well documented, such as the expected project. Okay. Software maintenance process models. Here you can see this is uh, software maintenance process model. First model in the area, this is software re-engineering. This is software re-engineering. Yeah, this is software. Sorry, software reverse engineering. This is software reverse engineering, and this is software re-engineering. Almost all the if the system is producing failures, too much failures, and prone to uh, risk, so we can do software re-engineering, which means that we we extract requirement specifications from the existing system, and from that existing system, from that SRS document, we add the change requirements, we add the changes of requirement needs to be done, and then carry forward with the same process model. Okay, again, software specification, design, module specification, and then code. So we extract from the code and add new or changing requirements, and then again make it a code. This is software re-engineering. Okay. Right. Elimination, estimation of approximate maintenance cost. We knew that maintenance efforts require about 60% of the total life cycle cost of the typical product. However, maintenance costs vary widely from one application to another. For embedded systems, the maintenance cost can be 2 to 4 times of the development cost. Here, Boehm proposed a formula for estimating maintenance cost as part of his constructive cost estimation model. Boehm maintains cost estimation is made in terms of quantity called annual change traffic. Boehm defined annual change traffic as the fraction of software process source instruction which undergo change during type. Okay. So annual change traffic can be calculated. Here we have the formula. Kilo lines of code added plus kilo lines of code deleted divided by kilo lines of code. Total kilo lines of code. Okay. Then maintenance cost can be calculated. We will find the annual change traffic multiplied by development cost. If I say that 100 rupees is the development cost, so maintenance would be, we can say that 1000 crores added plus 200 crores deleted divided by 1200, which leave us to by 1200, leave us to 1. Okay, so you can see the maintenance cost here is equal to 1 multiplied by 100, which is 101. Okay, this vary from each year to year. Also, we have to more maintenance cost estimation models, however, yield only approximate results because they do not take into account factors such as experience level of the engineer, familiarity of the engineer with the product, hardware requirements, software complexity. Right. Next, software reliability and quality management. In this model, we will see ISO standards and then capability maturity model. Capability maturity model. A repeatable software development organization is one in which software development process is person independent, which means like we have in non-repeatable software development organization, a software development project becomes successful primarily due to the initiative, effort, brilliance, or enthusiasm displayed by certain individuals. Thus, In a non-repeatable software development organization, the changes of successful completion of the software product is great extent depend on team member. Okay. So repeatable means it is repeatable organization means it is not dependent on a single person. They follow guidelines, standards. Then in non-repeatable organization, they don't have standards or guidelines to teach, sorry, to educate their engineers, so they will get they cannot produce more projects. Software reliability produces that as it can be defined as probability of the product working correctly over a given period of time. Reliability of a software product essentially denotes its trustworthiness or dependability. It can be also defined as probability of the product working correctly over given period of time. Okay. Which means that in SRS document itself, there should be a mention of uh, how long the software can get supports, how long the software can drain out, such as a hardware product like a car, like a bike. Same applies to the software. Even it is an intangible product, it is possible due to size, complexity of the program and storage problems, storage issues, adaptive. We change requirements frequently. Adaptive maintenance, adaptive maintenance. We change functionality, and then also in portable, we have to update the software into new port, new environment. Those can be added new errors that needs to be corrected. So which can affect the reliability of the given software. Okay. Here we can see one important fact here. It is observed by analyzing the behavior of large number of programs. 90% of the execution time of a typical program is spent on executing only 10% of the instruction in the program. These most used 10% instructions are called core of the program. The rest 90% of the program statements are called non-core and are executed only 10% of the total execution time. It therefore may not be very surprising that to note removing 60% of effects from the least used part of the system would typically lead to only 30% of the improvement of the system. What was given here is we knew that even if almost not all the users use 100% functionality of the system. Okay, such as if we take WhatsApp as an example, there are tools that almost not even used by a user. If you check your WhatsApp, you will find there are tools that is never clicked, that is never have been used by you. So in every system, there should be a core function or core source programs. Those source programs are executed 90% of the time. So if we reduce errors from that 10% of the source code, then we will get more reliability. Okay. Reasons for software reliability being difficult to measure. The reliability improvement due to fixing a single bug depends on where the bug is located in the code, whether it is in core or not core. The perceived reliability of the software product is highly observer dependent. The reliability of a product keeps changing as errors are detected and fixed. Hardware reliability versus software reliability differs. You can see the difference here. This is a hardware product. If you change, like you can say a we will say a car tire. Okay. A car tire have been brought after used, it will depreciate, it will get flat tires, it becomes flat. So here is the useful life. After the time, what we are going to do, we are going to change the car tire. Then After you can see it is used and then it is used. Now here we change the tire. So reliability again improves. But in software products, here you can see reliability just becomes absolute from time to time, because you can say we already state that fixing errors introduces new errors. In further cases, we have to fix those errors which leads to new error. Okay. So time to time, we will lose the reliability of the software. Then reliability metrics. Okay, we need to check the reliability metrics. We need to take time. Okay. So if you have any questions, you can ask, or we can wind up the session and we can meet tomorrow. Any questions?